cloud. Okay, hi. So, and I'll just put, I'm gonna do some Mathematica here also. Although, I don't think I have, let me just open this up. I put, oh yeah, I put these different Mathematica notebooks on here. So I might share some Mathematica stuff. I'll share screen if I do that so that the recording will pick it up also. But for now, let me just open these. So I have them. Okay. Something's happening there. We'll see what's going to happen. All right. Right. So we were looking last time, maybe I should go ahead and share screen a little bit. Okay, fine, thank you. Now let me share screen. Sorry, I'll get you. I got pretty, people had me last semester. I got pretty smooth at it towards the end of the semester last semester. It took me about 2.5 months, but I got there, right? So hopefully I'll get there again. Because we looked at things like this graph of this bowl shape, right? We were trying to understand the cross sections, the vertical cross sections, but you can see the slices and then now we just started talking about the horizontal cross sections, which are what are called the level curves or contours. And yeah, actually, this is interesting. So hopefully this is interesting. So, and I'll start right now. I'm going to write some stuff on the board in a second too. I just want to go ahead and think. These are various contours of the function z equals x squared plus y squared. So I'm basically setting x squared plus y squared equal to like certain values. So if I set it equal to like 9, I get this circle right here. If I set it equal to 4, I get that circle. If I set it equal to 1, I get that circle. Set it equal to 0, I get a point. And so, and this is supposed to be a little movie, but then they're supposed to be circles, but they're not rendering fast enough to actually be circles. So they look like polygons. Right, so let me go back to the board and actually write some stuff down. So, trusty chalk here. You're a true professional when you have a chalk case, your own personal chalk case. Okay. So, and special chalk. Don't worry, for students who've had me before, I can talk at length about Japanese chalk and how special it is. There's been like New York Times articles written about this chalk, so it's good stuff. So, okay, so let's go ahead and talk about level curves and contour maps. So, let's just start with this example. Z equals x squared plus y squared. And if we set z equal to various constants, right? So we've tried setting x equal to constants and gotten cross sections, x equal constant cross sections. We tried setting y equal to constant and got y equals constant cross sections. And so now if we're going to try to set z equals constant. So setting z equals constant gives us various what are called level curves or contours. Because now if we set z equal to constant, we actually get an equation in x and y, right? So example here, if we set z equal to 4, we get 4 equals x squared plus y squared, which you can draw, right, in the plane. It's a circle of radius 2. So, right, that's 2 right there. So that is a specific contour. And in the graph, in the bowl shape, it's really sitting at height 4. you know, there's a circle at height 4 of radius 2, like living within the surface, right? But you can also just draw it in the XY plane. Okay, and so, you know, as Z increases, we can think about how the level curves change. As Z changes, think about how the level curve changes for any specific example you're thinking about. And then in particular, we're going to plot level curves for a bunch of different Z's, and that's going to make the contour map, or the contour plot, sometimes it's called. So plotting level curves for, and I'll say this, usually when you see them, they're for sort of equally spaced. I don't know if that needs a hyphen. Maybe, I don't know, for equally spaced Z's gives the contour map. Right, so I wanted to talk about this example and another similar example and try to see, I'll hide the entire video so I'm not, see myself walking by. Right, so I'm gonna look at this example and I'm gonna look at a similar example and sort of compare them. So for specific Z, so for a specific Z in this example, maybe sometimes we would say like C, specific Z equals C, the contour or the level curve is x squared plus y squared equals C. What is that geometrically? A circle of what radius? C? Half C? Somebody say half C? Square root of C. Square root of C, right? The circle of radius square root of C. Yes, half of 4 is 2, but also the square root of 4 is also 2. So it's circle of radius square root of C, right? Circle of radius square root of C. So if we could actually just think about drawing contours, right? So like this color. So radius 1 would be something like that. And then radius root 2 is bigger, but not, it's supposed to be like half again as big almost. Radius 3, root 3, sorry. Radius 2. It's hard to draw, but this is, and so you can label the contours, right? This is like height 1, height 2, height 3, height 4, like that. But the circles are getting closer and closer together, right? So this is the contour plot. And the circles, so they're all the level curves are concentric circles centered at the origin, but they get closer together as we go out. As Z increases, right? And so, right on screen, I could show you a contour plot. Just copy this code. Oh, no, it's right there anyways. Okay. Right, so now this actually is doing them spaced at every 5, I think. Because there's 5, there's height 10, 15, 20, 25, 30, 35, 40. So that's the contour plot. And I guess the question is, can you see the bowl shape coming out of that? As you go away from the origin, what's happening? What's happening? How is your Z changing as you go away from the origin? It's positive, but it's also, what's also is happening? As I get farther away. Or what am I looking? I don't know. Maybe I'm not asking a well-formed question. I guess I'm thinking like, so it's going up, but we can say something more than just that it's going up, right? Yeah, well, it's not actually exponential, but it is getting steeper, right? It's getting steeper at each step, right? So like, yeah, because that's the thing to start thinking about when we start looking at these maps is like, level curves closer together means steeper if we're really doing this thing where we do equally spaced z's. You have to be a little bit careful about it. You have to look at the labels and make sure that's what's happening. Because I could draw something with sort of equally spaced circles, but the labels wouldn't be 1, 2, 3, 4. They'd be like 1, 4, 9, 16, right? So since we tend to draw these so they're equally spaced, contours closer together means steeper because you're going up. Like when I go from the 20 to the 25 contour, I'm going up by 5 in this distance. Whereas when I go from the 5 to the 10 contour, I go up by 5. You know, it takes me more horizontal motion to go up the same amount, so it's shallower, if that makes sense. So you can sort of see the bowl shape coming out of this. So steeper as we go away from the origin, it makes sense with the bowl shape. Okay, because I wanted to look at a slightly different example. Any questions about that, by the way? Just either start talking or just throw a hand up anytime. I like when students interrupt and are talkative, chatty. I mean, as long as it's about math. In office hours, it's fine if it's about other things, but here, if you have questions or comments or stuff, please don't hesitate. Yeah, those circles don't look like circles. All right, well that's, oh, actually, let me go back to the, stop the share and go back to the board. Okay, so let's compare this to a slightly different example. And because I want to try to think about what this surface is going to be, because it's a new example. I don't think we've seen, well, actually, one of the homework problems is sort of related to this, but so another example would be something like, what if we did z equals the square root of x squared plus y squared? That's a perfectly good function. We can plug in, I mean, it's worth noting that when we plug in x and y and compute x squared plus y squared, we always get a non-negative number, so it's okay, we can take the square root, right? You can't get a negative under the square root with x squared plus y squared. So now what happens with the contours? So let's think about this for a minute. Again, say z equals 4, right? We get 4 equals the square root of x squared plus y squared, which we could square both sides. And now what is that contour? Circle of radius 4, right? Circle of radius 4. So now if we did kind of similarly like we did up there, for a specific z equals c, the contour is c equals root x squared plus y squared. But that's the same thing as x squared plus y squared equals c squared. And that's a circle of radius c, right? So that's the difference here, is that it's the circles are now of radius c, and they're the same as the height instead of the square root of the height. Right, so that's the difference between the other example. That makes sense. And so now when we start plotting contours, the contour plot, the contour map, what's going to happen now? Well, we have height 1. I should draw the axes. Maybe I should have labeled the axes up there because I'm thinking this is 1, 2, 3, 4, right? And this is the contour at height 1. And then the contour at height 2. It's like that. The contour at height 3. And I'm running out of board space. So this is the contour at height 1, 2, 3, 4. And now what's the difference? Ah, you seeing a cone? That's interesting. People sort of see that. I was just hoping someone was going to say they're equally spaced now. But yeah, like, can you see what those are getting closer together as the increased. These are equally spaced as the increases. And remember, these are at height. This is a circular radius 1 at height 1, circular radius 2 at height 2, a circular radius 3 at height 3. You can kind of see it. And as you go away from the origin, right, you're increasing at the same rate all the time because the spacing is all the same. And so in fact, yeah, it's a cone. So equally spaced circles. It's a cone. Can you see it? Right, so trying to visualize that. If I go back to the Mathematica, so let me just put a square root in here. So yeah, so these are no longer getting closer together, right? And if we actually plotted the, where's the 3D version of this? Let me plot the 3D version, just so we really see it. So there's square root. This will work. Oh, what did I do? Oh, you know what? I need to change these. I can do -1 to 6. It's just, yeah. So do you see the cone? Why I taking it off strangely. Yeah, there you go. There's a good cone. Okay, so so that's the thing we're going to start doing is start building up this catalog of sort of things we're going to recognize. So now z equals x squared plus y squared, bowl, z equals square root x squared plus y squared, cone. Okay. And yeah, this is related. There's a question about on the homework about points that are the same distance from an axis in a plane or something. And I think there's some things here. Cool. Any questions about that? Okay. Let's do more examples. Where are my notes to myself? Right, okay. Yeah, I just want to kind of go through some more examples and just get us used to this, like how we play this game of sort of building things up. Yeah, so another example that we could sort of try to look at and try to draw the contour plot of, because that's the thing is like, you can think about the cross sections, you can think about the contours, and then try to rebuild the 3D picture in your head, right? Because you don't have a 3D graphing calculator in your head. Although, like, I think I said the Google search bar is a good 3D can plot 3D graphs and 2D graphs. There are programs now that do that like augmented reality thing where you can like put in an equation and it'll like you'll see the surface like on the table in front of you. So that's kind of fun to do too if you find an app. There was an app like that like a year or so ago. I can't remember now. You know, soon we'll all live in the metaverse, and then we can walk around in these surfaces and like walk through them and stuff. Look at them from every angle. All about that metaverse. Best in metaverse coins. Do it. All right. Okay, so another example. Let's just try this one. So this is one. It's actually going to be sort of similar to one we looked at last time. Z equals x times y. So I want to think about cross sections and contours here. It's just a nice example to think about for cross sections and contours. This example is almost always the answer to a problem on a test. And I'll get to what that problem is later, but I thought that might pique your interest. Okay, so what are the cross sections? So let's say x equals constant. For example, x equals 2. What's the cross section look like? What is that? If we cut the surface with the plane x equals 2, we get this, which is in a y, it's in a y and a z axis. So it's a line, right? You get a line. And then in general, for x equals c, we get z equals cy, line of slope c. So if c is negative, we can have negatively sloped lines. Yeah, in fact, sorry, let me share real fast. I think there's a good, we could do that thing I was sort of showing you last time of like, this is plotting, actually this is plotting, this is fixing different y values instead of different x values, but it's kind of the same, right? So these are what the cross sections look like as c increase, as here's the y value increases, right? You get negatively sloped lines and then 0 and then positively sloped lines. Okay, it's interesting. You get those in both directions. So similar for y equals constant. Question is, can you picture the surface those make? I don't think it's super obvious. No, good. I mean, it's good to admit like it's not obvious at all. Like we have something that's going like that, maybe like the lines of as they're moving, they go like that or something. Now we can actually do things in space because we're together. Okay, but keep that in mind. Maybe you can start to picture what it looks like. But then the point is going to be to build up different, perspectives and try to put it all together. So what about the contour map? If we set z equals constant, let's just say z equals 1, we would get like xy equals 1, right? What does that look like in the plane? I'm going to plot xy equals 1. What are you tempted to do algebraically with xy equals 1? Divide by x, right? So it's really y equals 1 over x. Same thing as y equals 1 over x, which you probably would recognize as like this. So this is the height 1 contour looks like that. It's actually 2 separate pieces. Could add in more contours like z equals 2 is just xy equals 2 or y equals 2 over x, right? Z equals minus 1 would be y equals minus 1 over x. So maybe if I draw some hash marks, this could help us a little bit. Am I still on the screen share? I totally still on the screen share. I got really good last semester about going back and forth between this, again, after about 2 months. So hopefully I can get back to it. Okay, sorry, so this is the board. So, right, xy equals 1 goes through that point. Xy equals 2 goes through the points 2, 1 and 1, 2. So it's like that. And then similarly like that. So it's something like that. A 3, maybe something like that. I mean, I think these all go asymptotically towards the axis, so they get closer together. They're sort of spaced in an interesting way here, but they get closer together. It gets sort of hard to label also, but find room to put, sometimes you do it, you just label like the ends of the, even here is hard, 1, 2, 3. Okay, and then -1 is actually over here, right? Yikes. And down here, like y equals -1 over x. And so on, -2, -3. What about the contour at height 0? We don't have the 0 contour here. What's the 0 contour? Somebody tell me. Is it both axes? Yeah, if x times y equals 0, then either x equals 0 or y equals 0, right? So yeah, both axes. So that's interesting. So sorry, z equals 0, x, y equals 0. So x is 0 or y is 0. So I can actually draw in the 0 contour is actually like that. Hard to draw in the picture, but. Okay, now the question is, can you start to picture this surface, what it looks like? These are the cross sections, the vertical cross sections. Here's the screen share. Oh, oh my God. I just gave it away. Did the wrong. Oh, I guess I had this. Well, this is like the movie of the contours again. Sort of interesting to think about. That's kind of going from negative, I think it's from -20 to 20. So going from height negative, if you're just slicing the surface, almost like a movie, trying to picture what's happening. You see that. Kind of interesting how they kind of come together and like at 0. You know, here's the full contour plot. Kind of what we were drawing there. Yeah, but then can you sort of see what happens again? Think about as you go away from the origin. If I go northeast or southwest, what happens? You increase, and more steeply maybe. I guess that's something to think about. Like, I guess they do get closer together. It's one thing to think about. I mean, they certainly get close together up here, but I think they get close together as you go this way also. And if you go northwest or southeast, you go down. So one direction you go up like this kind of, one direction you go down like this. We've actually seen that shape once before. Yeah, somebody say it loud. Saddle, there you go. It's a saddle. We had, last time we looked at x squared minus y squared, and that was a saddle. This is actually almost like a 45-degree rotated version of that. And it's interesting though, because again, all the slices are line, all the like vertical cross sections are lines. But you get a saddle. And so that brings me to the question that I ask on tests a lot of times, which is, suppose every x equals constant and y equals constant cross section of a surface are lines. True or false? The surface must be a plane. It feels like it should be true almost, right? Like if you have lines this way and lines that way, it feels like a plane would. A plane certainly does that. If I have a plane and I cut it, either way I get lines. But this is an example of that's not being true, it's false. Z equals xy. All the cross sections are lines. Either way you slice it. But the surface is not a plane. So that's a nice example. Cool. But yeah, it's kind of hard to put together. Like, can you put together the movie of like this movie that was up here, you know, of the cross sections in a certain, you know, those are the y equals constant cross sections. Can you sort of see the saddle shape being swept out through space as those turn? It's not super easy, but it's something to work on building that skill. And then again, the contour plot you can see from above, right? If I sort of turn this that way. Yeah, it's like, that's the contour map right there. You can see it from above. Okay, so we're building up. All right. Any questions about any of this so far? Let's do another example. Maybe I'll give you guys more time to think about it and try to tell me what's going on, rather than me just doing the work. So I think on the screen there, you can probably. So the z equals x squared plus y was the next one I wanted to mention. And then, yeah. And then we can talk about when a variable is missing. That's sort of an interesting case. And then we can talk about linear functions. So yeah, anyways, I think we're doing okay. But this is just example after. You just have to do examples to start to build up like a feel for this stuff, right? So I said z equals x squared plus y. So think about, I want you to think about the x equals constant cross sections, the y equals constant cross sections, and the contour map, the contours, the level curves. So do all these, start thinking about them yourself, but maybe just like, I don't know. Everyone turn and introduce yourself to someone near you in the classroom. Awesome. So now the people you just talked to, work with them on this. Think of, like, kind of try to figure out what the x equals constant cross sections are, y equals constant, and the contour map. So do all those, and then see if you can put it together and see in your mind what the surface is actually going to look like. It's no fun when I just lecture the whole time, right? People figuring things out. Oh, by the way, this is recording, but the only microphone is this. There are ceiling mics, but it actually, when both mics are on, it messes up everything. Don't worry about your voices being recorded, like for posterity. Say all the stupid stuff you want because nobody's recording it. Only my stupid stuff gets picked up. So what are these? X equals constant cross sections. What do those look like? Somebody want to volunteer? You almost look like you want to volunteer, but I don't want to force you to. It's up. Yeah. They're just lines, right? Because you're plugging x equals constant here. And what's true about all the lines? They're just all slope 1, right? So these are lines of slope 1. I suppose the intercept is always positive because it's x squared or non-negative. I think I have that right here. Just I'm letting y change and I'm fixing values of x. So, comes from out of the picture. So that's interesting. The y and the z axes are not. Or the x, wait, what is this? Yeah, y, this is yz. I guess I could have just done -5 to 5 to make it more. Okay, so those are all lines. That's interesting. Okay. Now what about the y equals constant cross sections? What are those? Oops, I just gave it away. Sorry. Is that what you guys found? They're parabolas, right? They're all x squared plus constant parabolas. That's just going straight. Those are just going up, right? Parabolas. Z equals x squared plus constant. Can you see the surface from those? Anybody have a feel for the surface? Try to see what the surface is from. Do those go together? I mean, do the two pictures go together? Like, that's a hard thing to think about, like why one cross sections are lines and the other are parabolas. I see some looks of consternation, which is good. What about the contours? What are the contours? Like what's the contour, the z equals 1 contour or something like that, or the z equals 0 contour? Anybody? Yeah. Try. Yeah, we get c is x squared plus y. So y is c minus x squared. So when we do the contours, looks like let's see if this works. Where did they go? Oh my God. Yeah, -20 to 20 was not necessary. Let's go to share. Those are, again, it's not rendering fast enough to make them nice, but oh my God, come on. That feels very slow to me. I feel like it should be smarter than that. Okay, anyways. So negative parabolas as you go up. So we could try to draw something like that, right? What am I doing? I guess I was drawing like a box, like a actually, why would I draw this when well, I'll draw this because then you'll draw it. Maybe that's the reason. So I just show stuff on the screen. Students tend not to. Okay, so right, so we just get these negative parabolas. I'm not drawing these that great, but especially since the vertex is supposed to be there. So let's say that's -1, height 0, 1, 2, because it's basically, that's the intercept, right? So now this is the top view. Can anybody describe the surface? Can you see it? Can anybody see it? What does it look like? Yeah. Yeah. Oh. What's starting soon? Oh yeah, please. Like a tunnel? Some sort of like tunnel? Like a cylinder kind of tunnel, or? Sorry, what's the word? An archway tunnel. Oh, interesting. So like, yeah, this is a top view, but yeah, this is sort of like going down or going up. So it's like good. That's good. What anybody else? I was saying there's not much hype, but what's starting like next week, this week? What big global event is starting this week? See, I said it's not been hyped very much. No one? The Olympics are starting. What does this feel like? This feels like something in the Olympics. Yeah, like a half pipe maybe or something. Here, let me get some code. Oh, let me switch back to the share also. Okay. You know, I really should just be pausing the share, probably not unpausing the share. That's actually probably the smarter thing to do. So what was this, x squared plus y? Let's try this. Ooh. I'm doing some slightly strange. Maybe let's make it taller. Yeah, it's kind of like a, like a half pipe or something, right? I mean, it goes on forever. And yeah, you're good, I think, upside down, but it would be like an archway if you turn it upside down, like a tunnel that you'd be going through. So yeah, do people see that? Because on the one hand, I mean, in fact, I think the best way to see it for me is the, what is it, the y equals constant cross sections. Basically just being a bunch of parabolas that are, you got these parabolas in space that are going up like this. And so that makes your nice like half pipe, whatever kind of thing you're looking at. Or, yeah, and it's kind of weird that these are negative parabolas. I mean, that's a little bit of a weird thing to try to convince yourself that that's actually what would happen, that the points at the same height would actually make like a negative parabola, but it's, well, there it's plausible, right? Yeah, if you were gonna walk along the points at the same height, you would sort of get to a max point and turn back around, go back down the other. It's weird how the size changes on these as you move it. Okay, so yeah, so this is interesting. It's just kind of the kind of things we're starting to get used to. Maybe the last thing I'll say today, because we only have a couple minutes left, is just what if you only have functions of one variable? Like, what if we just had z equals x squared? When y equals constant, what do we get? If y is 1, what's the equation become? Z equals x squared, nothing changes, right? It actually doesn't care about y. So y equals constant, we get all the same. Z equals x squared, parabolas. So we get actually just parabolas going back and forth like this. Actually, now that we're actually in a physical room together, we can think about it. So this is the origin. The x-axis is down there. I'm screen sharing, aren't I? Damn it. I need to like pick a student who's going to yell at me and tell me like, of course the camera's not going to follow me over there, but yeah. So if you look at the bottom corner, I think of the origin down at the corner there. I think of the x-axis being along that wall, the y-axis down here, and the z-axis up there, and then this is the y-z plane. That's the xz plane over there, and the xy plane is the floor. So if you just think z equals x squared, basically in the y, okay, the y doesn't matter. So in the xz plane, you just get the parabola z equals x squared, and then you just move it back and forth like this. And so you also get like a trough. I guess it's not a half pipe because it's not going down anymore, but it's like a trough, right? X equals constant cross sections is sort of interesting just because like you get z equals constant. Does that make sense? If I have this trough that's like this in the room, like because there's the x-axis down there, x is here, and I have a trough like this, and I said x equal to constant, what do I get? You just get like a line along the trough, right? Like a specific, like you're cutting the trough. If the trough is like this, you're cutting it this way and you're just getting a line. So it's sort of interesting just to think about like what kind of things can happen. So the book actually calls these cylinders, which is weird, but it's kind of like how a cylinder, the cross sections are always the same, they're circles in a certain direction. And you can sort of think of this as a quote unquote cylinder. I don't know. I'll just say like, that's the word the book uses when a variable is missing. Let's quickly, just before we're out of time, just let me show you examples of these. So yeah, if I did z equals x squared, if I get rid of this plus y, then right, it's just an infinite trough going both ways. It's basically whatever is in the xz plane, just move back and forth along the y-axis. If I wanted, so maybe you can try to picture sine y. If I change this to sine y, can you picture it? What's it going to be? Someone over here talking. Can you guys picture it? Sine y. No, I did way too much of z because sine is always between -1 and 1, right? Yeah, it's just an actual wave, like a 3D wave, right? Just going in that one direction. Because it's like in the YZ plane now, you would have the sine wave, and then you're just moving that back and forth along the x-axis. Could have been helpful if I labeled the axes here, but oh no, I did. Yeah, so there's the x-axis down there. It's hard to see. And then here, the x-axis is this way, and then the y-axis is on the trough. Okay. Okay. So what we have to do Wednesday is linear functions and functions of free variables. But yeah, we're out of time. So thank you guys. I have office hours right now downstairs. My office is first floor, opposite diagonally. like the opposite corner of the building from this. I stopped the recording. I also have office